Hello, everyone. Hope you all are doing great. This is Shaurya from SSERD, and I welcome you all on the sixth day of the World Space Week program by SSERD. Hope you all are enjoying this Space Week with us by participating in various workshops, keynotes, and competitions organized by our team. And after a wonderful session on challenges and opportunities in satellite-based industry by Mr. Narayan Prasad from Set Search. So today we have a second interesting keynote coming up that is on space of communication satellite and interplanetary internet by Mr. Nitish Singh, co-founder and CEO of Astrogate Labs. He is a former team Indus engineer in Google Lunar X mission. He has completed his BTech plus MTech in aerospace engineering from IIT Kharagpur. He, along with Mr. Aditya Kedlaya, started Astrogate Labs. Founded in 2017, Astrogate Labs is a space technology startup from Bengaluru, enabling high-speed communications for small sats. Astrogate is developing small sat terminals and optical ground network for full turnkey solution for all satellite and optical communication needs. They intend to build the entire chain of optical communication system and to cater to global markets with their high-quality products related to space infrastructures. It was a great honor that you accepted our invitation, sir. I welcome you on the screen.
Thanks for the introduction. And it's actually a pleasure of mine to be talking about a topic which we are very much passionate and interested on and actively working toward. So having said that, I think we'll just jump into the keynote here.
Yeah, you can start sharing your screen.
So, so one of the major things I want to talk about is why the current space communication infrastructure is just not sufficient or our even on the lower space needs, as well as if we talk about exploring further out to cislunar and deep space networks. As you know, right now most of the commercial activities right now is on the low Earth orbit satellites, mostly micro and small satellites, which is increasing at an exponential rate. Owing to the increased number of these satellites, as well as uh, the data generated from each one of these satellites, we are looking at congested RF spectrum. These spectrum just is not enough to get a satellite enough data down. If we talk about exploratory missions, we are looking at around 10 Mbps of an average speed from cislunar and less than MB speed from a deep space mission. So this relates to a very low data return for your exploratory missions, as well as the cost is humongous because you have to put heavy infrastructure on the ground, on the terrestrial side, bigger antennas, as well as on your satellite one size. There will be RF antennas, and as you know, as you move further across, if you want to go to Jupiter as well, your antenna size increases, and you are farther away from the sun as well, so your power solar panel size also increases. Uh, the cost becomes exponentially increasing as you go across. One more major challenge right now is just from a total RF standpoint. We are just looking at RF ground stations, RF antennas putting up. These infrastructure only allows low contact period. So you're looking at satellites coming up, and for one pass duration, which is around 5 to 7 minutes, you will do particular ground station antenna. You can obviously scale that up, deploying multiple antennas across the globe if you have that sort of a cache around you, but it's not an efficient use of resources. There's also physical limitations. This is mostly we cannot scale this network. We cannot get on-demand access. If you want to schedule a ground station pass, you will have to either do it 12 hours or even weeks in advance, depending upon what type of satellite and what type of antennas you're using. So as we are seeing a increase in the smaller satellites constellation, we need also rapid access to these satellites. Think about is we are making a phone call. I can reach anyone in US right now. Can we make a network like that which can easily reach or communicate to space assets as well? How do we build such a space communication network? Well, one of the key things is you have to think like right now on the physical layer itself, which mostly is RF spectrum. There have been deployments across laser communication links on the commercial one side. The European Data Relay Satellite has done that for typically low Earth orbit Earth observation missions for ESA. There is also, you know, about a mission uh, on the LLCD Lunar Laser Communication Demonstration developed by NASA. That's the first mission that is out in cislunar space of 622 megahertz. That's proved the norm, and now people are setting up multiple constellations of these satellites in an active program, trying to set up constellations. Other major challenges of space communication is the turnaround delay, like that you cannot combat around anyways. We're talking about delays from lunar distances to around 2.5 to 2.6 seconds, and out to Mars you will have over around 40 minutes turnaround delay. So these networks needs to be self-reliable. They should be automatically acquired, and that's what we are building, and I'll talk about in a few minutes. One of the other paradigm shift that has happened in space is talk about traditional space, which is basically bigger class of satellite developed by space agencies or even on the defense fund side, which costs $300 million, more than 3 years to build, test, and deploy. But right now, most of the commercial activity, including what we are looking at, is addressing these challenges from a smaller satellite perspective. Talking about size, satellite which is around a backpack, will takes almost 9 months to build, test, and put it into orbit. $500,000 to one satellite. So you can deploy these satellites large number, and you can take advantage of the miniaturization on the sensors on site on electronics, address much of the challenges closer to Earth. This is how we are doing it. So we have what Astrogate is building a whole space communication solution mostly on the optical communication side, and we are setting up first on the low Earth orbit. So if you have a satellite right now in space and you want to communicate better, you can actually plug in your Astrogate communication. And the few pieces to this is one is obviously an Astrolink terminal. This is basically a satellite communication hardware. You can readily integrate it into your satellite. And instead of working on an RF spectrum, we work on the unlicensed optical frequency. So we are able to push much more data down. It's also unlicensed, so we are saving on the cost, as well as the beam is not narrow. So laser beam pointers are like very fine beam that inherently has a multiple challenges also to accurately point it, but you get much more secure solution as well and a much more optimized power solution in that. So this terminal you can readily integrate on a satellite to provide up to 1 Gbps over link from a low Earth orbit. Plugged into that is obviously a ground station, which again we have built the product on size and we're deploying these ground stations in the next year. So these are small aperture ground stations which can get the data down from your satellites on an optical link. And in the phase two, we are expanding on more on in-orbit relays. Do it, and this is some rationale that I've already established out. There is a limited amount of infrastructure that you put on land and still not get an on-demand access for satellites. In order to do that, you have to put in orbit relays. So these are our phase two deployments where we would be putting satellites equipped with our terminal that can offload data from nano satellites, small satellite constellation, and then can finally push it to our ground station. Where are we? We have completed the terminal development. So this is one of the industry's smallest, offering up to 1 gigabytes per second downlink on a license band. The key technologies that were developed in-house, one is obviously the laser beam, precision control and pointing. We're able to control at very 5 millidegree precision pointing of the beam. We are also doing one mission later next year on a SpaceX Falcon 9 rocket, where these terminals would be proven for a space to ground link. Some more tests that we did. So we have qualified this for space use. So we qualified it for the launch roads that would be facing it and then it flies up into space. And this is our first mission. We are already on track to build this. The terminals are developed. We are integrating on the satellite part in the next 6 months, testing that out, and then it will be flying on a 3U nano satellite mission, again deployed by us by December 20. Followed by, we are also doing a space-to-space communication demonstration. That would be the roadway for us to do second phase of relaying the data from a nano satellite to our satellites and then beam it back down. Uh, that's what I have. I will mostly want to address more questions you have right now.
Thank you, sir,
Yeah.
for that wonderful session. So let's move on to Q&A. We will be picking
Pertaining.
up some questions from live broadcast. Uh, so we have our first one. How do the communication delays between interplanetary missions is reduced? Any futuristic solutions for this problem?
So one of the problem is obviously you cannot break physics. So that's how the microwaves are propagating. You cannot break the speed light limit. Nothing you can do about that. But what is to be done is building a network that can relay the data uh, back from intermediate satellites. So we're talking about scheduling ground stations right now, if you want, and that depends. Like you have to point the ground station antenna at a particular location when you want to communicate with the satellites. So that has to remove. There is an fully automated ground network and the space network solutions that are being pictured into. In fact, you should look at on the NASA scan program as well, which they are doing another mission, lunar communication demonstrations actually. So that's the step that we can take to further delay it down, and you can get the messages. You will get it obviously much later, 40 minutes down, but you will get it on your.
Cool. So what are your future missions for Astrogate Labs? Like, what
Yeah,
are your
so
plans?
one of the missions that we are already working towards is our space to ground first satellite that we are flying in December 2021. This is a 3U satellite. Will be equipped with our small satellite terminal, and then we are deploying the ground station because obviously you need that as well to the space to ground communication. And that we are putting up in Australia. We are part of the incubation, only in station Asian Space Tech be part of the venture capital space program in Adelaide. There we have collaborations work in place where we are deploying the first ground station. And then further on in 2022, we are looking at commercial deployment of these ground stations and further relay satellites.
Great. So talking about more Astrogate Labs, in how many countries are you working right now?
So we have activities right now going on in two countries specifically. So one is obviously India, Bangalore, where we are running most of our R&D activities. And the ground station is what we are deploying in Australia. We have activities in Australia.
Okay. Mm, yeah, we have another one. What happens when the satellite in seeing the Earth lost its communication?
Can you repeat that question, please?
Yeah. What happens when the satellite seeing the Earth lost its communication?
So yeah, there are basically two basic need of communication. One is obviously to have at least command the satellite and know what sort of a health parameters you can get down. And if you have a failed link on that, there's nothing too much you can do about it. But if the link failure you're talking about is much more on the high speed payload data link, where you're getting mostly instrument payload data, that you can quickly recover. Mostly these scenarios are worked on to eliminate, not to actually work on like what we will do next. If the communication losses happen and you still want to communicate the satellite, then that you can't do much.
Yeah. Mm, yes. Another one we have. How much it costs to build small communication satellites?
So, well, mostly I'll talk about more on the small satellite and form factor. So if you're building a solution around that, a per satellite cost will, including the deployment, like really putting it for the launch cost and all, you can do it around 500,000. And that's then that's on the upper side. So that's mostly related to that. If you are looking at building a bigger truck size satellite, I guess you will have to have multiple $1 million or at least work with the space agency.
Yeah. Uh, yes. What will be the future of communication satellites?
So future, we are looking at more a communication network. So these are multiple satellites forming a network where you can have on-demand access. What I mean by on-demand access is right now, the best analogy I can give is like you want to do a phone call, you can easily reach a particular person on Earth, but it's not simple for communicating to a particular satellite. You have multiple things to think about. Where is your ground station at? When actually that particular satellite will pass over that ground station? When you have that exact geometry to figure it out? When you will have a communication pass and schedule it? These can be eliminated by having a hybrid approach where you have terrestrial assets, you have in-space assets to relay data from low Earth orbit or even beyond. If we talk about interplanetary network or even Mars. So these technologies are actually being worked upon. There are multiple demonstrations going around throughout the world.
Great. So it was. mm yeah, we have another one. Is there a method to tackle the signal delays during interplanetary missions?
So yeah, I think it's a similar question that's been answered before. But yeah, so what we can do about is let's say you have a rover on Mars, right? And you want to communicate it back to Earth. There's only particular geometries that will allow that. What you can have is instead of having that mechanism, put certain relays. So you have an orbiter that relays the data from your the rover back to the orbiter, and then again Earth rotates, right? So one ground station network will not suffice it. You have a three ground station network. That's already in picture. Actually, DSN ground station networks have you see, they have uh, around 120 degree apart in three complexes. Those ground stations. But further than what you can do is there are separate link layer protocols that is to be implemented, where once the packet has been forwarded by the rover data, it can be recognized by the orbiter and then finally send it to a particular destination location without any human intervention or any human operations for that satellite. So that's the way you can delay it and make it much more reliable.
Great. So, do you work on other satellites like remote sensing and military spying?
No, we are not working on the remote sensing satellites. We are working mostly on the communication equipment and the satellite. And so I think a better person who does that would be.
Yeah, this question is interesting. Do communication satellites communicate with each other? Do they share the data between them?
Yes, they do. So in fact, the communication satellite itself, you need to have communication for them to know exactly what they are doing. In fact, the link, but you don't need to have a separate link. And there's also two sort of links. One is obviously we'll have a low data rate link to command the satellite and know what it is up to. And then there are a particular high bandwidth uplink which we are putting it on the optical links right now, which can transfer the data across. And that's some of the methods that are actively being looked at.
Yeah. Uh, Another one we have. What are the major challenges facing satellites and C bands?
So these are basically any RF spectrum right now that you're using is most congestion prone, and it's not. It's basically the boom has happened, and we are seeing a paradigm shift on multiple satellite constellation because of the miniaturization of this, and we can do multiple nano satellite constellation. So the problem mostly is coming from as the number of satellites is growing and the data demand is going up, have much more better spectrum allocation done. And there are not too much of a spectrum that is going on. There are other spectrum which sort of conflicts with your 5G terrestrial network as well. So those are the things. But anything specific to C-band? No. The problem is overall on the whole spectrum itself.
Yeah, great. So it's another. How does interplanetary communications affects efficiency?
On the efficiency one side, I mean, what sort of efficiency which part of efficiency are we talking about?
Uh,
We're talking about
that
efficiency
I
of how
can
the
cannot say
communications
about,
would
like,
would.
because we are, yeah, it can be
Yeah.
about anything because we are just taking these questions from
All right. All
outside.
right.
So uh, Yeah, how does the communication satellites are different than other satellites?
Mostly depending upon where you're putting it. First is a communication satellite. If you want to have continuous access to the Earth or have a longer access to a pure orbit, will be a bit different. And depending upon the orbit and the lifetime period, you will design that satellite accordingly. Other than that, what happens is you take about current geostationary communication satellite, they need to constantly communicate with Earth, right? So in that case, that the prime mechanism where it is in terms of the location of the satellite as well as the power generation. That's yeah, uh, you have to take care of that. Other than that, communication satellite need to point at a particular location again. Depending upon where the satellite is again relaxed or can be much more constrained because you want the RF beam to be at a particular spot.
Nice. Yes, what is the average life of small communication satellite?
So again, I think mostly I will talk about the small satellites in low Earth orbit, and that low Earth orbit we are talking about mostly 500 to 550 kilometers up above. So that's a lot of. But still, there is some aerodynamic drag that degrades the orbit and moves it down. Uh, so those sort of satellites are mostly restricted uh, on the time duration in the orbit, how quickly they can decay. They can range to around 3 years to 5 years. And the other side of the problem is obviously you need when you're tracking on small satellites, you need to take care about space radiation, all those aspects as well, which can increase. If you're talking about satellites which are up on the geostationary side of things, well, there you are more worried about the electronics and all that lasting. So people design those satellites around 50.
Yeah. Uh, yes. Can the CubeSats act as repeaters for interplanetary missions?
Can you repeat that question, sir?
Yeah, sure. Can the CubeSats act as repeaters for interplanetary missions?
Actually, yeah. So if you look at Marco, which is the satellite launched by NASA on the InSight mission. The problem with the InSight lander was when it was during the course of years, EDL, which is entry, descent, and landing of that, uh, it was not in coverage of the Earth. So they put a few systems like Mark A and Mark B, which sort of relay the data from that and then beam it back across. So that's one of the instances where these satellites have put up into interplanetary space.
Yeah. Um, yeah, this is a long question. Why doesn't NASA put a network in the sky with each orbiter, rover, space-borne telescope, and any other skyward launch device working as well?
They are doing that. Actually, they are in plan to do that, and they but you have to understand like there are multiple pieces of technology in this that's being demonstrated. So the first piece of technology is obviously what sort of physical communication medium you will use, which for mostly interplanetary distances and bigger distances, laser communication is the way to go because you can save much more on the satellite size, weight, and power of all your communication equipment. And obviously, you're doing a very narrow beam, so you're very dedicatedly pointing it to the Earth to communicate it. The laser communication demonstration has been done on the protocol layer that I was talking about, like how a particular packet can be rerouted automatically. In terrestrial framework, we are mostly aware of the internet TCP/IP protocol, but that doesn't work in space because of the large delays. So if you are bouncing our packet right now, it will reach on another satellite maybe in another minute or so, up to an hour or so, depending on the distances. So that sort of protocol will not work. So people are working on something called a disruption or a delay tolerant network. In fact, NASA has done the demonstration with lunar laser communication. This protocol on an optical channel. They're also doing a relay demonstration, CRD, EDRS, and all that. They are also so they are already putting it. Thing is, it takes time to do all that evaluation.
Yeah. Yeah. So let's move on to our next question. How does interplanetary internet works for different countries? Like each country have their own connection or they are worldwide?
When we're talking about interplanetary internet and this one, where the vision is basically to combine the terrestrial communication infrastructure to your interplanetary communication. So there is no distinction. Let's say if I want to communicate to a satellite right now, I can use that infrastructure to route my data across that. So how it is.
Great. How far off we are from real-time signals or communication, say from Jupiter to Earth?
I would say we are pretty far, but the pieces of the technology are there, already being demonstrated for the longer range. In fact, right now, as I said, communication distances on optical communication to distances has been done. We are also expanding to deep space. There are missions that have been planned across to do optical communication from Mars distances. So that's the link that you will use in a sense. But in order to have a real-time access, you need to have multiple intermediary spacecrafts there which can relay the data down. So, yeah, that is far. I think mostly we should focus right now on the lunar demonstration.
Yeah, and this is about our India, where India stands in context to interplanetary internet.
Sorry.
Where India stands in context to interplanetary internet.
I mean, India as a whole obviously is a more a space technology one focus. So every agencies, including ISRO and all that, are focusing on that. But if you're looking at combining the terrestrial infrastructure and space communication infrastructure right now, that's pretty. But as I say,
Yeah,
that the developments on both the protocols that you want to use, the systems you want to use, the architecture you want to use, those sort of developments are already going.
so let's take our last question for the day. How can we make communication and internet cheaper for the use of everyone on Earth?
So one of the thing is obvious is you will see mostly from satellite communication constellations. We are able, everyone is aware about the Starlink constellation. They are beaming global broadband data, which is a smaller cheaper rate in a sense. But again, it's the economy scale from how cheaper can we make the satellites, right? And how cheaper we can, how quickly we can roll out the spectrum, and how those technologies are there. So there are ways to make the internet cheaper even delivered from a satellite. And that's primarily to get down the cost of the satellite, which includes the satellite development cost as well as the launch cost, which is you will see that has already gone down more than 10 years in 5 to 6.
Yeah. Thank you, sir, for this wonderful session, and we will wrap our keynote on this. And I thank you for attending this, for giving us such a immense knowledge on the satellites and interplanetary internet. And I thank you from the whole SSERD team. Thank you for joining us for celebrations of World Space
Thank you.
Week.
Thank you. It was a pleasure to talk about something that we are actually doing.
Yeah,
Thank you.
thank you. Thank you very much, sir. So we are not yet done for today. We have a third interesting keynote coming up at right 6, that is on interstellar gases by Professor Jayant Murthy. And our competition Star Wars is also happening right now. So you can check it out for the third round. And if you haven't gone through our website, do check it out. And here's a good announcement for you guys. We are coming up with our new programs, and we are launching our new courses for school kids on various topics that are life beyond Earth, space, math at beginner and advanced both level, with the rocketry and space exploration. Their content is updated on the website. You can check our website, that is www.sserd.org. And don't forget to like and subscribe this channel and share it with your friends. Till then, bye bye. Take care.